So hello everyone, I'm Silvia Popa, a second-year PhD student, MPA. So at the start of the week, we heard several talks about population analysis from gravitational wave observation. And that's definitely the way we want to go forward if we want to better understand the physics of binary black hole mergers. But we can also learn a lot from individual systems, especially if they stand out and challenge our current models, as we also heard from talk by Yixian. So GW231123 is definitely also such an event. It originates from the most massive binary black hole merger. And this is what I want to tell you about today, and also presenting our work that was accepted for publication in APJ letters 2 days ago. So this is a gravitational wave signal. It's very strong. It was observed by both LIGO detectors, as the name says, on 23 November 2023. But even though it was observed back then in 2023, it was only recently announced this summer. So let me highlight what makes this event so special. Here you can see the masses of the primary and secondary black holes using different waveform models. And because this is such an extreme event, it's more susceptible to systematics, reason why you also see that not all models actually agree with each other. But let's stick with the quoted masses of 13700. And if we compare this with the inferred mass distribution of the astrophysical black hole population from the observation so far that peaks around 10 solar masses, we can all agree that this is a very extreme event, placing the black holes within and also above the mass gap. So this is also interesting that one of the black holes might lie within this upper mass gap where we do not expect the formation of black holes from stellar physics. So finding a black hole in this gap means that we either have an incomplete understanding of how we think about these massive progenitors, or the universe finds other ways of forming these black holes, for example, through dynamical mergers. But this is only half of the story. What's also very interesting about this event is the extreme spins with individual curve parameters of 0.9, 0.8, meaning that the black holes are almost maximally spinning. This is also much higher than what we expect from dynamical mergers, where the peak would be at around 0.7. There are people that are not very optimistic about how well we can constrain the spins, because this was a very massive event. We only have 5 cycles. But let's go with it. Let's say that we do see this event, including very, very massive, highly spinning incoming black holes that are quite unlike anything we've seen before, and also not what we expect from our current understanding of binary black hole mergers. Nonetheless, after the detection, there have been several papers that try to push the limits of our formation channels and investigate if we can reproduce these extreme properties. Some of the people are in the audience. You can talk to them if you want to know more about these channels. I will instead focus on the stellar physics interpretation, where the idea is that the incoming black holes come from the direct collapse of very massive, highly spinning progenitors. And I told you before that we have this upper mass gap. Maybe we even have a region where we shouldn't form black holes. But if we consider rotation, Gottlieb, in the context of this event, showed that if you start with a highly spinning helium core, you can actually form a highly spinning black hole within the mass gap. This is because rotation gives you extra support in the outer layers of the star, meaning that they are not directly collapsing, they are forming a disk instead, and mass can be then ejected through outflows or jets, populating thus the upper mass gap from above. There have been studies that focus on the evolution of individual progenitors, but of course, we need 2 black holes. We need a binary if you want a merger, and this is what we address in our work, where we explain this event through chemically homogeneous evolution. So let me tell you about this channel. So the CAG channel starts with two massive stars in a very tight orbit. Tidal forces are very strong, so the stars are synchronized. They are tidally locked, like 2 dancers holding hands, so they're forced to spin around quite fast. The deformation by rotation, but also the one induced by tides, induces efficient internal mixing, which makes that the stars evolve chemically homogeneously. We do not see a chemical gradient. And this has a very a drastic impact on how these stars evolve. They do not expand as in normal evolution. They instead stay compact. They form helium stars, and at the end, black hole binary mergers. So the predictions from this channel is that the black holes have high spins because we start with highly spinning stars, at low metallicity because there we have very, very weak winds, so we can keep the angular momentum we started with. So thinking about very massive, highly spinning black holes, this channel is one to consider. So this is what we did. We used the MESA, the 1D stellar evolution code, to create this grid of binary models, binary CAG models. I won't go too much into the details. We are at low metallicity, assume equal mass binaries. We use the main assumptions in the MESA code. The stars are tidally locked during the main sequence, but we assume that tides become inefficient once they contract into the helium stars. We evolve the models until helium depletion, and then we assume direct collapse with a total mass and angular momentum conservation. So this is our grid. Here you can see we use different initial masses. We start with different initial periods. The models in the color are the models that are evolving chemically homogeneously. Here in black, we have systems that are so close in the beginning that they merge. If we go to two further initial periods, then they do not evolve chemically homogeneously. But most importantly, the systems indicated by the squares are the systems that whose final masses at helium depletion match the masses of the black holes from the event. But what we're interested in is, of course, the final spin and the masses of the systems. Here you can see what we got from our models, and if we compare this with the properties from the GW231123, we do have some candidates that reproduce the very high spins and high masses of the incoming black holes. What we were also surprised to see was this very tight correlation between the spins and the final masses. We start with their very different initial masses, very different rotations, but at the end they all follow this very tight trend. And what we discovered, or what we looked into that, we noticed that actually our progenitor stars are reaching critical rotation. This is because the stars spin up when they form helium stars, but the main influence comes from the fact that they get very luminous. They almost attain Eddington luminosity. So this critical rotation actually sets this very strict limit on the spins. Analytically, you can also understand this if you just compute the spin of a critically rotating star, where you plug in the angular momentum of a critical rotating star, and you have some dependence on the radius, luminosity, gyration radius, and these CAG models follow very, very strict trends. So using the scaling relationships between the radius, luminosity, and mass, you actually get a very tight correlation between the spins and the mass, which explains this downward trend. So coming to the conclusions, of course, there's open questions remaining. What happens in the final stages of black hole formation and collapse is quite complicated. As I mentioned, you can form a disk instead of direct collapse. So this is still remaining to be investigated. There's also the questions of how common these progenitors are in the universe that remains open, but I hope that I convinced you that when coming to massive, rapidly rotating black holes, the chemically homogeneous evolution channel is a viable formation channel. And if you don't believe in maximally spinning black holes, this is observational evidence that there's a killer spins in the local universe at the residence. So yeah, thank you, and I'm happy to take questions.
Questions for Silvia? Thank you.
Thanks. Do you also, since your stars are critically rotating in your MESA models, do you also enhance their winds, like due to rotational?
Yes, that's exactly what happens. So I have a plot. Sorry, this is the... Yeah, here you can see the evolution of the mass. So that's exactly what happens. They do not... So we are very, very low metallicities. We don't have actually winds, line-driven winds. But we do have this mass loss exactly due to rotation. So MESA tries to get rid of mass in order for the star to remain below this threshold of critical rotation. Yeah.
So if you have a chemically homogeneous scenario for this, you would also get effective spin of 1, right?
That's not what our models show, no.
Okay.
So in this scenario, I mean, some of the models do have spins of 1, but...
Sorry. I just meant large chi effectives. Right?
Yeah, okay, yeah, that's totally fair. Yeah, so, yeah, that's a good point. So you could have maybe some misalignment due to some kicks when the black holes form or something, but it's true that this channel does lead you to high chi effectives, yeah.
Hi, wonderful talk. My question is very basic, and it's just because I don't have a good intuition. How low of metallicity do you need to be for CHE to allow you to do this?
Yeah, so here in the models we go very, very low metallicity, but there's a grid of these models, and you have to be somewhere between SMC and LMC.
That's much higher than I thought.
Yeah, I can show you in the break, so I don't have the plot, but I can show exactly the limit where this thing still works. Yeah.
Thank you. Under 30%?
On the question of the chi-effective, actually I wouldn't expect high values because the spins, of course, are very high, but these are extremely heavy black holes, and to tilt them, to tilt the plane will be very, very hard. So
You would not
it should be high.
It should be high, yeah.
From the models, it should be very high because they're not tilted.
There should be a line,
yeah.
Yeah.
But if they're aligned, you wouldn't have it off side. Am I?
No, I think
We're saying the same thing. Okay, all right.
Right. So I think what Pedro is saying is that they're not going to be misaligned. Right. So Vicky's saying they're not misaligned, and Tejo is saying that observationally the claims are that if you trust the LVK spin measurements, then they actually are misaligned.
So I grew up in a world where direct collapse, mass was conserved, etc. But then working on this over the summer, Gottlieb and other papers, the actual collapse of a fast rotating star into a black hole will not be a direct collapse. And so there's very nice simulations. She showed one of the plots with different amounts of magnetic field. There would be material thrown out. If you have a significant fraction of the mass lost in this process, I don't know what the spins do. Let me put it this way. I'm hopeful, because then this would explain the most event if it's real. But yes.
Okay, so we'll take one more question while we're handling this question. If all the rest of the speakers for the session could come up, we'll continue with some more discussion.
Okay, so if I'm right, the 231123 happened at relatively low redshift, right?
Yes.
Like 0.4, was it?
Yeah.
So do you expect the delay time from when you collapse these massive stars to be close to a Hubble time, or do you think the progenitor would have formed very late in some very low metallicity, low mass dwarf galaxy?
Actually, these models have very, very short delay times.
Yeah.
They merge very quickly because they're very close.
Yeah.
But I mean, this is just one metallicity we chose. If you go at higher metallicity, they would possibly widen further. So have a bit, or yeah. I mean, there's different channels also. Like if you widen too much, then there could be a triple star that could make them then merge. That's another project I've been working on. So it's, yeah, but I mean, these models are merging very fast.
Yeah, okay.
Yeah.
All right, let's thank Silvia again, but don't run away.